Okay, welcome to the last session for today. We will have two research talks, and our first speaker is Bratati from University of Buffalo.
Thank you. Thank you everyone for showing up, and thanks to the organizers for giving me this wonderful opportunity to speak about acylindricity of outer automorphism group of some bumps-log solitaire groups. So let's recall what are these groups. The bumps-log solitaire groups. These are some one-relator groups with two generators. And we are only interested in the non-solvable ones. So we're ruling out all the bumps log of this form, 1n. And throughout the talk, the assumption would be Q is bigger than or equal to P, and that's strictly bigger than 1 because I'm ruling out this case. And goal for this talk is actually, I want to talk about three things mainly. And I'm going to define what these mean. So the first is, of course, we are going to talk about the acylindricity. Of these groups. And the second one, if we find acylindrical actions, then can we find largest such action? And the third part will be talking about quotients of these groups. So preserving acylindricity of these groups by some quotiented by some nice subgroups of them. And what do I mean by nice? I'll define that later. Okay, so first, a little bit of motivation. Why do I care about out BSPQ? And to be very honest, I was working on a totally different project where I had to deal with out BS or out GBS. And then separately, we were learning about asymmetrically hyperbolic groups. So these groups were in front of us. And a natural question to ask was, what about the acylindricity of these groups? And turns out, after doing a little bit of searching in the literature, that people have been thinking about these. So a very well-known example of acylindrically hyperbolic groups are out FNs, of course. And Genevois actually also thought about automorphism group where it turns out to be acylindrically hyperbolic. So if G is one-ended hyperbolic group, then the automorphism group of G is acylindrically hyperbolic. And he has another result with Horbes, where they showed that if G is infinite-ended, finitely generated group, then also the automorphism group of G is acylindrically hyperbolic. So we can think about these kind of questions, like what kind of conditions we can put on G so that the automorphism group or outer automorphism group of G is acylindrically hyperbolic. And I also forgot to define what out G is. Probably everybody is familiar, but out G is just collection of the automorphism group quotiented by the collection of inner automorphisms, which are basically automorphism by conjugation. All right, so now let's go back and recall the definition of acylindrically hyperbolic groups. So definition, whenever I'm talking about acylindrical action, then I am assuming G is acting on a hyperbolic space by isometries, and I will call that action to be acylindrical. First, I'll give you the formal definition. If for any epsilon bigger than 0, there exist two constants, so both of those depend on epsilon only, such that if I have 2 points in the space far apart, and by far I mean they're at least distance r apart, then what happens to this collection of group elements who keeps x in a epsilon neighborhood and also keep y in its epsilon neighborhood? Number of such elements are bounded above by this number n. So there's an uniform bound there. What's happening here really is if you take long geodesics, like roughly, if you take long geodesics in your space x, you consider the epsilon neighborhood, then only finitely many group elements are coarsely fixing those long geodesics. So I have gx, gy. Only finitely many of those are keeping it within this epsilon neighborhood. So only finitely many group elements fix long geodesics coarsely. Okay, so now that we have the definition of an acylindrical action, let's talk about acylindrically hyperbolic groups. Now, Osen has classified this acylindrical action. So it can be either elementary ones or non-elementary ones. And the elementary means G has bounded orbits, or it's virtually Z. And we are interested only in the non-elementary ones. So definition, G is acylindrically hyperbolic if it admits non-elementary acylindrical action on some hyperbolic space. Okay, now by non-elementary, I mean I have lots of independent loxodromics. And loxodromics are also known as hyperbolic elements if you're familiar with that term. And by independent, I mean if I have two elements, G and H, then if I am tracing to the boundary, then they should give me distinct points. All right, for example, if I have our F2 tree, it's a 4-valent tree, and I have the horizontal direction to be A and the vertical direction to be B. If we take any element in F2, that's a hyperbolic element, and any two elements, loxodromic elements, are independent there because there are no loops, right? So everybody's gonna go to the different boundary point. All right, so with that, oh, I have one more, okay. Let's come to the first point where we talk about the acylindricity of the group. And this work is by Matt Clay. So Clay actually gave a group presentation for the out BSPQ when P divides Q properly. By properly, I means Q has to be a multiple of P and N cannot be plus or minus 1. Okay, so he used the theory of deformation spaces, and yeah, I'm not going to talk about the deformation space today, but if anybody wants to talk, yeah, I'll be happy to talk about it later. So this is the deformation space. For now, we can just think of these as connected simplicial complex. A very celebrated example of deformation space is the Collar-Vogtman space. So out Fn acting on CVN, that's an example. But he did not work with this whole deformation space because that's not always tree. He wanted a nice tree to have action of this group. So he managed to get a deformation retract of this space into a nice tree. So this is a tree. And what deformation space is, it is collection of all BSPQ trees. So here in this tree, the vertices are again trees. Okay, so it's a tree of trees. Then I have the out BSPQ action on that tree, and using that action, he came up with this presentation for out BSPQ when P divides Q properly. And the other cases when P doesn't divide Q properly, those are not really interesting because those are either finite or virtually cyclic. So those are never going to be acylindrically hyperbolic. So this presentation is a amalgamated product. With one free factor to be a finite group. The other one is infinitely generated. This has a semi-direct product with Z2, and the edge stabilizer is again finite. So here the semi-direct product means like everything has that semi-direct, that factor, Z2 here. So it's really, when we are thinking about this action, it's sufficient to consider only this bracket part. Okay, so using that group presentation, because the edge stabilizer is finite, we can look at its action on the Bassett tree and find out that that group is acylindrically hyperbolic. And in fact, those are relatively hyperbolic. Professor Indra Chatterjee first pointed that out to me, so thank you. But we were interested in the action on that deformation tree, rather. So we wanted to see whether that gives us acylindricity of the group and that has enough loxodromics or WPD elements. So we were interested in the action of this on the tree. Turns out that action is not acylindrical, but nice enough. And by nice enough, I mean it's a non-elementary WPD action, and if this doesn't make sense to you, that's okay. So there are different ways of showing acylindricity of a group, and that's another equivalent way of showing it. To give acylindricity of out BSPQ when P divides Q property. So it's an if and only if statement. Out BSPQ is acylindrically hyperbolic only if and only if P divides Q properly. All right, so both of these methods give us the acylindricity of the group, but this gives us an example of a group where the group is not acylindrically hyperbolic, but the out G is. So BSPQ, that's not acylindrically hyperbolic. But here in this statement, we get the out G, out BSPQ is acylindrically hyperbolic. Now, once we have the acylindrical action, or the acylindricity of the group, we can talk about many different acylindrical actions on hyperbolic spaces, right? So which one to consider? So we want to consider the best one, and best one meaning capturing more information about the group. So for example, if I consider the Cayley graph of a group with respect to the generating set to be the whole group, then the Cayley graph becomes a complete graph, right? So if we consider the Cayley graph of a group with respect to itself, and we lose all the geometry, right? So we don't want that kind of things. So this is by Carolyn Abbott, Sahana Bala Subramania, and Dennis Olsen. So they have defined partial ordering on this set of co-bounded acylindrical actions. On hyperbolic spaces, and this in some sense encodes how much more information the action tells us about the group itself. And if there exists, with respect to this ordering, if there exists an equivalence class of acylindrical action that is larger, well, first of all, it should be comparable to other classes. Not always that happens. So it is comparable and larger than the others. Then we call it the largest action. Okay, so actually not all acylindrically hyperbolic groups admit a largest action, And one good thing about having largest action is eccentricity, whether that's quasi-asymmetry invariant or not, we don't know that. So in other words, if it's a finite extension of the group, if we can preserve the eccentricity or not sure. But if we have a largest action, then we can ensure preserving eccentricity under finite extension. So that's a very nice consequence of having a largest action. And we were able to prove that this out BSPQ, again, when P divides Q properly, admits largest acylindrical action. And that's not just the existence, but the largest action will be on its Basser tree. All right. So that's the second point. Now moving on to the third point where I want to talk about the quotients. And this actually, I think, comes from Thurston's Dane-Filling theorem for three manifolds, and where he talks about having a three-manifold compact orientable and then doing the Dane surgery, so drilling out a solid torus and then gluing back another solid torus but with a homomorphism. And Thurston talked about if you have this manifold after drilling out, so you have the torus boundary, then when after gluing back, if you're starting with a hyperbolic structure, finite volume, then when you get the hyperbolicity back after gluing back the solid torus, right? So that has a very nice counterpart in the theory of relatively hyperbolic group, and more generally in the world of asymptotically hyperbolic groups. So again, this is something that I would very much like to talk about if anybody is interested after the talk. But from there, actually, this question comes from there, whether we can preserve the eccentricity under quotienting, or in general, even that, I think the first thing was preserving relatively hyperbolic groups, but then to the world of eccentricity. And this was the work by Damani, Hagen, Sisto. They showed, again, mapping class group is an example of asymptotically hyperbolic groups. So they showed, okay, I'm doing either genus bigger than 0 or punctures bigger than 3, then the mapping class group quotiented by these subgroups, these normal subgroups of mapping class group, preserves the acylindricity. And what are these? These are generated by, so this is a normal subgroup generated by kth power of Dane twists. And this is for suitable case, so not for, okay. All right, so in a similar setting, Matt Clay and Johanna Mangahas worked on the quotient where for more general, a general group acting on here a group is acting on something called a projection complex. We are not going to talk about that here, but you can assume those to be graph for now. So if we have, starting with a non-elementary WPD action here, which means, okay, projection complexes are quasi-trees, so they are hyperbolic. Now, if the group G is acting nicely on this projection complex, then the group itself becomes asymmetrically hyperbolic. So if we are starting with that, then they showed something called the subgroup generated by equivariant L-spinning families, which comes from this setting. If we quotient by those nice subgroups, then you can preserve acylindricity of this group for, again, suitable L. All right, so from there, because the out BSPQ has a nice action on its Bassett tree, and trees are by default projection complexes. But this theory actually takes a simpler form in the world of trees, because the L spinning families become spinning families, and that is not covered here. So what are spinning families? I have collection of subgroups of the vertex stabilizers, and they satisfy, so I should write equivariant spinning families. So they should satisfy two things. Equivariance is basically preserving, like, compatible with conjugacy. So equivariance means the RGV is going to be basically conjugation by G. And the spinning condition, it takes a particularly simple form in case of trees. It's basically if you have a vertex and then an edge is adjacent to it, then RV cannot intersect the edge stabilizer. So it should intersect the edge stabilizer trivially. And what we showed was when we can preserve the acylindricity of out BSPQ by quotienting by those spinning families. So out BSPQ quotiented by the normal closure of RV is acylindrically hyperbolic if and only if the tree corresponding to it, if we look at the quotient tree, then that has to be infinite. That means I am able to preserve the loxodromics that I need to conclude acylindricity of the quotient group. I think I'll stop there. Thank you.
Any question for the speaker?
Yes. It's not acylindrical. I think you can show, so particularly, so if you remember the definition of acylindrical action, then long geodesics cannot be like fixed by infinitely many group elements, right? So in our case, we were not finding any uniform bound on fixing like long geodesics. So that gave us. Correct. Yes, yes, yes. I mean, you will understand if I draw the tree here. Yeah, basically in the Bassett tree, like in the tree we had a ray. In the Bassett tree, that actually becomes the fundamental domain, like of an edge. So whatever was not acting nicely there in the Bassett tree we were able to manage like that. Actually, that rules out. So yeah. Yes.
About this largest action,
Yes.
can you maybe say something about why it's useful and perhaps examples?
The consequence that I mentioned is like, the asynchronicity. Yeah, the asynchronicity is not preserved under quasi-isometry, but in these cases, you can like either like finite index subgroup or finite extensions. You can ensure that like those are preserving the asynchronicity. There are others, but these are the ones that I am mostly interested in. Yes.
It's preserved under finite extensions. That's only known when there's a largest action.
Yes.
But it's conjectured that it's preserved under finite extensions in general. Is that correct?
I'm not sure about that, if it's conjectured that. Yeah, I know like many people are working on that, but yeah, I'm not sure.
So in general, if you QI to distribute
Yeah, that's still open.
do you know in this specific case if you QI to out? Yes.
I don't know. Yeah, I only can say like finite extensions and finite index subgroup.
Any more question? Okay, then let's thank the speaker again. Should we